So in today's video we are going to learn with respect to a concept called as the defects. So before knowing the term defects, first of all we have to know that where does it arise from. Remember guys, in this chapter we saw that we were mainly dealing with the solid state of a matter, and basically we were dealing with respect to a crystalline solids. Of course, in our lab classes we have just seen that how to prepare this crystalline solids, and also I have shown you certain crystals. And the greatest example you can also see in your dining table with respect to that of your NaCl crystals. But one important thing you have to remember that, so whatever the crystals we are preparing, they are not in their purest form. Even the crystal, when you are taking as a crystal, for example, in the general representation of a crystal, we draw as a cube, if you are remembering, in each and every cases. Remember what happens means in this cube, of course, these particles will be arranged in their face, in their corners and everywhere. But what happens whenever you are preparing a crystal, they will be embedded with certain impurities other than the main constituent particles. For example, if NaCl can be embedded with that of your SrCl2, strontium chloride, there may be a possibility. So there is no crystalline solid which is ideal in nature, that is of the purest form, of course. So whatever the impure form is there, we are going to mainly deal with it with certain names in this concept under the topic called as the of your defects. So first of all, we have to understand that what are the two types of the defect which arises here. So mainly there are two important types of defects. One is called as that of your point defect, and another is called as that of your line defect. So point defect means what? The defect is arise within the close appearance of that atom. Here, anywhere. If for example here is one more atom present, this may be some other defect which is arising with respect to this part itself. But when you are coming with respect to the line defects, remember it will be along either one diagonal or whole one row. A single from the one line when you are drawing, overall that line will be having certain top of it defects. So such defects will be called as a of your line. Whereas a point defect means the defect which will be arising with respect to the corresponding atoms itself. It's like a point surrounding part. In a line defect, the defect will be arise along the line itself. So such type of defects will be called as a of your line defects. In our chapter, we are mainly going to concentrate with respect to that of your point defects. So this point defects is further classified into two important types. One is called as that of your stoichiometric defects. Another is called as that of your non-stoichiometric defects. So we are going to deal it by one. So once again, these stoichiometric defects have been also known as that of your thermodynamic defects, have been classified into that of your vacancy defect and the interstitial defect. So this stoichiometric defect, first of all let us know that what do you mean by this stoichiometric defects. Of course, the defect which is not going to change the stoichiometry of your solid. If it is of the ratio, for example NaCl is 1:1, of course if it is having any defect, the ratio will be 1:1 itself. No changes will be observed in its stoichiometry. Such defects will be called as that of your stoichiometric defects. Mainly there are mainly two types, vacancy defect and interstitial defect. In order to give the explanation for vacancy defect, let me first show you how the vacancy defect would look like. So basically if you're just seeing your textbook, they are given you this part. So this is an example of the diagram what they have given as that of your vacancy defect. I mainly use it because they are having a color representation. It will be easy to notify. If these are considered that of your constituent particles, we could just see that there are some empty spaces in the vacant sites in the lattice sites. So such type of a defect is called as that of your vacancy defect. So how can you define it? The defect which is arising due to the vacancy in their lattice sites, such defects are called as that of your vacancy defects. Is that clear? But the most important noteworthy point we have to remember, and we are going to deal with, and of course which is going to appear in your exam, is that of your interstitial defect. So interstitial defect may what happens, in an interstitial defect, whatever the effect or the defect you are going to see, they will mainly with respect to the interstitial positions, of course, which I am going to deal in a couple of minutes. So first of all, this interstitial defect is once again classified as that of your Frankel defect and that of your Schottky defect. Schottky defect. And also one more you are having, which is also called as that of your impurity defects. Let us go now one by one. Remember, in this Frankel and Schottky, of course, this is a pakka question. They can ask you the difference or they can ask you any one type of a defect in a brief note. So first and foremost, you have to understand these two defects in a proper way. So first of all, in interstitial defects, we have classified them as that of your Frankel defect, Schottky defect and impurity defects. Let us now come with it. How does it look like? So basically you have to remember that Frankel defects agli athwa nimma Schottky defect agli, they both are occupying or they are appearing in that of your ionic solids, having both your cation and the anion. So in Frankel defects, what happened? You can just notice this diagram. So what we are saying, you are having plus, you are having minus, you are having plus, you are having minus. This is an ionic solid. But in this position, we could just see that there is an absence of a positive charge. But due to the absence, what you can just notify one more over here is, this positive charge has been occupying an interstitial site in between these ions, which is called as that of your interstitial site. Able to see? So what is happening? Mainly whatever the migrating or whatever the leaving ion will be there, that will be of a smaller size cation. So such type of a defect is called as that of your Frankel defect. What is happening? In an ionic solid where the cation leaves its lattice site and occupies the interstitial site. Such type of a defect is called as that of your Frankel defects. Mainly you can see this one in AgCl, in AgBr. So these are mainly seen with respect to that of your silver chloride agirbodu, silver bromide agirbodu, zinc sulfide or silver iodide. You can ask me, so why only these solids? Because whenever you are choosing their size of the cations, Zn2 plus agirbodu, Ag plus, they are having very small size. And that results in the arising of a defect called as that of your Frankel defect. Very much important and noteworthy point. Coming with respect to that of your Schottky defect, remember, it is also appearing with respect to that of your ionic solids itself. But what happens over here? Here, both cation as well as an anion are missing from the lattice. They are not present itself. They are not occupying the interstitial site. Instead, what is happening? Both cation and anion will be missing from the crystal lattice. So whatever may be the number of the cations missing, the same number of the anions would be missing. For example, you could just see over here. Here one cation is missing, one anion is missing. In the same crystal, you can also observe that here also cation is missing, here also anion is missing. So there are total that 2 cations are missing. In order to make the electrical neutrality, 2 anions are also missing. Remember, both in Frankel defect and in the Schottky defect, we are observing that they are maintaining the electrical neutrality. Even here the plus charge was missing, but it is occupying within the crystal lattice a positive charge. Therefore, it is neutral itself. But what is happening in Frankel? Whatever the leaved site is there, that is the vacancy it is creating in its original site, instead it is occupying an interstitial site with respect to Frankel defect. Coming with respect to Schottky defect, what it is trying to say, here both cations or anions are missing from the crystal lattice. So such type of a defect is called as that of your Schottky defect. Very much important and noteworthy, you have to remember it. They can ask you the difference or any one type of a defect in brief note. Examples for that of your Schottky defect, of course you can just see your NaCl, your potassium chloride, your cesium chloride, your silver bromide. Once again I want to note over here an important CET question. Your AgBr and shows both type of a defect. Frankel defect to show madutte as that of your Schottky defect nu show madutte. Very much important, noteworthy point you have to remember. Coming to another type of an interstitial site is that with respect to that of your impurity defect. So coming with respect to impurity defect, let me first show you how the defect would say. So basically, if you are preparing a crystal of NaCl, as I given the example earlier, so what happens over here is, while preparing a NaCl crystal, there will be some amount of strontium chloride goes into the crystal. But what happens over there? Here, two vacant sites of NaCl will be seen. But what happens? In that only one site, your strontium will be occupied. But also it maintains the electrical neutrality. Can you think why? What is the charge of Na+? Of course, it is +1. When it is leaving two sites, that means it has been created a +2 charge with respect to the overall crystal. But the incoming is a strontium ion, and one strontium ion is having just +2. So it is enough. If 2 moles of that of your Na+ is moving out, only 1 mole of that of your strontium is enough in order to make the crystal neutral. So such type of an impurity which has been creating a defect is called as that of your impurity defects. Here also you can see with respect to that of another examples like your cadmium chloride, your silver chloride. Your silver chloride also shows that of your Frenkel defect. It also shows with respect to impurity defects. Remember what is happening? Ions are missing, of course, your cations are missing, but in turn to balance the ions missing, what happens? Only one ion will get replaced and another site will be left vacant. So such type of a defect is called as that of your impurity defects. So these were the defects which will be coming under that of your stoichiometric defects, in which there is no stoichiometric change. Of course, Na2 plus was which was moving out. In order to balance that one, Sr2 plus have come. There is not a much change. Overall neutrality is maintained. But coming with respect to that of your non-stoichiometry, remember there are mainly two important types. One is called as that of your metal excess defect, and another is with respect to that of your metal deficiency defect. With respect to non-stoichiometry, that means what? There will be change in the stoichiometry with respect to these defects. This metal excess defects once again has been categorized into two important types. That is due to anionic vacancies and that of your due to extra cation. Due to anionic vacancy, that is here there will be an anionic vacancy, and here due to the extra cation. So remember guys, I would just like to show it here. One of the most important thing we have to see with respect to that of your anionic vacancy, which is called as that of your F center. First we'll understand that what is happening over here. Coming over here, let us take a crystal, F center crystal they have given you. I'm just taking an NaCl crystal. Remember, NaCl crystal. So if I'm going to heat this, assume that this electron is not here, instead here was an atom itself, chloride atom itself first. So what happens? First, when you're heating this crystal in the presence of that of your sodium vapor itself, so what happens? Your chloride ions which was present over here, it tries to diffuse out. When it's coming in out, it is coming as a Cl minus. So in turn that Cl minus will try to react with the sodium, neutral sodium atom, to form as that of your sodium chloride. But we know that if Cl minus has to attack sodium, sodium has to lose one electron in order to form as Na+. Then only this Na plus and Cl minus will be giving you as NaCl. So what happens? Of course this reaction takes place. So whatever the extra electron what the sodium has left out, okay, it will try to once again come back, and the incoming electron will occupy the position of the chloride ion which has earlier diffused out. So what happens over here? The anionic vacancy which was created will be occupied with respect to the electron which has been given out by your metal. So such anionic vacancies which is occupied by an extra electron is called as that of your F center. Very much important. So the anionic sites occupied with respect to that of your unpaired electrons are called as that of your F center, which means what in a Greek word Farben-center, that is a color center. Now you may ask me why it is called as a color center. Here they give an example. For example, if you are going to heat like this crystal, that is which is having an F center, what happens? This crystal appears to be color when you are heating it. Why is it happening so? I have given you the explanation when we are treating with respect to that of your calcium salts and that of your strontium salts. So these electron on heating occupies or it absorbs certain energy and it jumps to the higher energy state. It remains unstable and again it tries to come back, and when it is coming back it will emit the absorbed radiation, and that radiation will be falling under the region of that of your visible light, in turn making over the whole crystal as that of your colorful. That is the reason it is called as that of your Farben center, which means a color center. That is the reason that of your LiCl also appears to be crystal, appears to be pink, and excess of potassium chloride also appears to be that of your violet. That is mainly because of this extra unpaired electron which is occupying that of your anionic vacancies. There's a 1 mark question. They can ask you that what do you mean by F center? Remember, such type of a defect is mainly observed in that of your alkali metal halides like your NaCl, KCl, or that of your LiCl. Coming with respect to another defect which in this metal excess defect is that of your metal excess defect due to presence of extra cations. So what happens over here is when you are heating this zinc oxide, it will be giving you out the oxygen and extra Zn2 plus will be occupied within the crystal lattice. And due to this extra cation, your overall zinc oxide crystal appears to be somewhat yellow in color. You can just see the stoichiometry over here. Instead of being as ZnO, here the stoichiometry has been changed to Zn1 plus X. That is due to the excess of this Zn2 plus ion, which has been moved to the interstitial site. And due to this stoichiometry, it results in that of your colorful of the crystal. But also the electrical neutrality will be maintained, because here whatever the Zn2 plus will be occupying the interstitial site, the neighboring site will be occupied by the electrons which your metal has been lost, and in turn the charges will get balanced and you are having the overall electrical neutrality. This is with respect to that of your metal excess defect due to the presence of the extra cations. Coming to the last part with respect to that of your metal deficiency defect. Of course, in a metal deficiency defect, I would only like to explain it because in textbook you will not be able to look after. For example, if I am taking an iron oxide. So when I am trying to see its stoichiometry, of course, whatever I have written, you can observe that it will be 1, you can save. So it is 1:1. Of course, it is not. When I am seeing its stoichiometry, I could just observe that it is having a ratio of 0.93 to 0.95. This is the range of the iron present in this crystal, and the oxide, of course, it is 1. Now the question arises, why such defect is there? Remember guys, whenever you are taking an iron oxide, there will be both the forms. Fe2 plus will be also there and Fe3 plus will be also there. So certain cationic sites will be occupied with respect to that of your Fe2 plus ion. In the same way, certain cationic sites will be occupied with that of your Fe3 plus sites. So in turn making its stoichiometry to be somewhat less than that of your 1. So what is happening over here is there is a metal deficiency. Instead of being 1, it is being less than 1. And that is creating a deficiency of the metal. So such type of a defect is called as that of your metal deficiency defect. So this completes the overall defects, that is stoichiometric and that of your non-stoichiometric defects. And in the next video, we are going to see one of the most interesting part called as that of your conductors, semiconductors and insulators. And we are going to detailedly learn how these semiconductors are synthesized for our better usefulness.